Assalamualaikum and good day to all of you. So today we'll learn about new chapter. It's actually lecture 11. So the new chapter is distributed coordination based system, and this slide is based on the distributed system principle and paradigms book by Martin Van Steen and Tannenbaum. So in this topic, in this chapter, we are exploring how distributed system coordinates and unlike standard communication where processes talk directly to each other. So coordination in the system will focus on how processes cooperate and share data in a more decoupled way. So one of the biggest challenge in the system is not just sending the messages, but also coordinating how multiple processes can work together when these processes are running on different machines at different time and with different knowledge about other processes. So now under coordination model, the essence here is we are trying to okay, let me change the pointer first, sorry. So we are trying to separate computation from coordination. So coordination deals with all aspects of communication between processes as well as their cooperation. So here we evaluate this model using two types of coupling. So basically in distributed system, coupling refers to how tightly two processes are linked to each other. So basically um, the goal of coordination is not to have a tight couple, but the goal of a coordination-based system is decoupling, meaning we do not want to have a tight coupling. We want to have a loose coupling. Where decoupling means allowing process to work together without being dependent on each other. Because when processes are independent from each other, so that is so much better. Okay, that will make coordination much more easier. So there are two types of coupling, which is here temporal coupling and also referential coupling. So for the temporal coupling is all about time. So the question here is, do both processes need to be active or running at the same time to communicate? So basically, here if two processes are coupled, okay, are tightly coupled, so they must be both running and active at the same time to interact. So if the answer of this question is yes, meaning the system is tightly coupled. But if the answer is no, so basically they are loosely coupled or decoupled. So basically, if they don't have to be running at, if two processes do not have to be running at and active at the same time to communicate to each other, so one can leave a message, one process can leave a message and go offline, and the other can read it later. So this is kind of like the message queue. And then we have another type, which is referential coupling. So do cooperating communicating processes know each other identity explicitly? So basically here, if the answer is yes, meaning if in order for them uh, to do something, to communicate, they need to know about the identity of the other process beforehand. Okay, so if the answer there is yes, meaning it is referentially coupled, and if the answer is no, meaning it is decoupled, meaning they can the process can communicate with each other anonymously. So in this diagram, this table, we can say table, shows four quadrants of interaction across two coupling dimension that we have discussed earlier. So the coupling dimension is temporal and also referential. And here there are two states, which is two coupling state, which is coupled and also decoupled. So basically, if we look at the top left here, in which the intersection of referential coupled with temporal coupled, so we will get direct. Okay, we will get direct communication, meaning if both of them are uh, um, uh, when temporal couples and referential couples intersect with each other. So what it means is both processes need to be alive and know each other. This is something like phone call. So need to be at the same time. And then the second one is the second quadrant is temporal decoupled and referential coupled, meaning both of the process A, process B, need to be active and running at the same time. Okay, but uh, but sorry. This one is decoupled. So basically, temporal decoupled means both of process A and process B uh, they don't need to be alive at the same time, but they need to know each other. They need to know the identity of the process. So the application is like email. So like email, you need to know the address, the identity of the sender and recipient, right? So basically, but uh, you can send an email and they don't need to reply on instant. Yeah. So next we have the next one, temporal coupled. Temporal couple mean two process need to be running at the same time, but they do not need to know each other. These two process. So basically, the the analogy is like meeting oriented. So process don't know who they are meeting. You just get an email, so you need to come to the meeting, but you don't need to know everybody in the meeting, but you are meeting at the same time. And then we have another one, which is generative communication. So generative communication is like the goal of the coordination system, meaning it's all decoupling. So process do not know who they are talking to and they don't have to be active at the same time. They just generate data into a shared space. So basically this diagram visualize a different form of coordination, and the losers one is the losers bukan losers LOSERS, tapi yang paling uh, yang paling loose adalah generative communication. So basically hence the reason many of the distributed coordination system distributed coordination based system like Linda or Java Space are using the generative communication model. So here, um, this is the architecture of distributed coordination system. So a data is described by means of attribute, uh, that and okay. So before I explain this, I just want to explain that this diagram is publisher subscriber model, publisher subscriber architecture, not architecture, publisher subscriber model. Okay, so first let us understand first the some of the key concept. So a data item is described by means of attributes, and when made it available, it is said to be published. So here in this model, so we have the data item here, and then we have the data items, which is the main component in the model. So here, this architecture introduce powerful concept in which you do not always need to communicate each other through each other, meaning you may not always communicate to other process directly. Okay, but you can communicate through topics or content. Yeah. So in this case, a process, if when a process interested in reading an item, so they must provide a subscription. and a description of the items it wants. So basically here, that's why this is the publisher subscriber model, meaning if a process, which is the subscriber, so we have two subscribers in this diagram. So if they are interested in reading any data item, so they must subscribe first, and they must tell the description of the data item that they want. Okay, so publisher will generate data item, but they don't send the data to specific process or users. So what they do is they just publish. So they publish it here. Okay, so the black dots, so they publish the data item uh, with certain attributes to the middleware. So they publish it to the middleware. So then the middleware, which sits between the subscriber and also the publisher, they will act kind of like matchmaker, where the middleware will match the published items and subscription. So basically, when a new data item is published, it checks all active subscription. Middleware will check all active subscription and notifies or deliver the data to the matching subscriber, because in the first place, in the beginning, subscriber already said that they are interested in certain data item. So basically, subscriber doesn't know who the publisher is. So it's the job of the middleware, which is the matchmaker, to match the data item and the interest of the subscriber. So this is often used in large-scale systems such as stock tickers, newsfeed, IoT, event-driven system, because it removes direct dependencies between producers and consumers. Next, we look at the coordination model of one of the most famous example of a distributed coordination-based system, which is Genie or JavaSpace. So basically, JavaSpace is a high-level coordination tool, and it's used widely. It is used widely globally in distributed system to allow multiple processes to communicate by sharing data in a common area. So, so basically, if we want to achieve, we do not need to actually build it ourselves, so we can just use the JavaSpace, because it already provide the tool so that process can communicate directly without knowing each other. So what happened here is JavaSpace will provide shared repository services where data is stored until it is needed. So basically, if you have heard Apache River, so JavaSpace comes from Genie. And if you have heard of Apache River, but now Genie is known as Apache River technology. So JavaSpace, earlier I have mentioned that Linda and JavaSpace implements generative communication. Let us look at the coordination model. So temporal and referential uncoupling. So temporal and referential uncoupling or decouple, which is the generative communication by means of JavaSpace, a tuple-based storage system. So a tuple is a type set of reference to objects, and tuples are stored in serialized, that is marshaled form, into a Java space. So basically, in simple terms, a tuple is just a row of data or package of information. So you can think it like digital container that holds a specific set of values grouped together. For example, um, if you would like to in JavaSpace, if you want to store information about student, for example, right, you don't just send the name, but you need to send the student tuple. So for example, if you want to talk about student, this example is tuple, so you need to talk about student John Doe, the name, and then the metric number, and then the program. Okay, so and then we also have to read the tuple, so we need to construct a template. So construct a template with some field left open. So basically here, for the for the template, we need to match it against a tuple through a field by field comparison. Sebagai contoh, for example, so we see here student. So field 1 is the type. So then we get the string student, and then field 2 name, and then field 3 ID number, and this one field 4 is the program. So we need so basically this is how uh, to construct the template. So the tuple space, Java space, is the bucket where all these tuples are stored. So next, let us look at the operation, junior operation. So here we have the operation which is write, and then read, and then also take. So for write, what? So basically for write, a process will create a tuple instance. Okay, a process will create a tuple instance. So this one A, yeah, okay, as process A, tuple instance, and insert a copy of it, a copy of A, so into the Java space. So in the diagram, process A and B are adding their data to the central cloud, which is the Java space. For the read, a template is compared to tuple instance. So the first mesh returns a tuple instance. So basically, a process that needs data creates a template. So basically, this template acts like a search filter with some field left open. So the system will compare the template against all stored tuples here, field by field. So I already explained tadi, field tadi just now. And then take is like a removal. So a template is compared to tuple instance. So the first mesh returns a tuple instance and remove the matching instance from the Java space. So this is kind of similar to read, but the difference is once the first mesh is found, the system returns the data and remove it from the Java space. So Java space. So basically kat sini, if you look this process, so they look to put the mesh T and return, but when it mesh, once the first mesh is found, so they return it and remove it from the database. So there's no longer C here. So in the distributed system, okay, this is another distributed system which is TIB rendezvous. So, or usually we call it TIBCO RV. Okay, RV is rendezvous. So it's a high performance messaging middleware that allows different applications to exchange, to exchange data across a network. So basically, TIB means the information bus. Yeah, so because this looks like a bus network topology. So the key here, this diagram, the key here, the coordination model in TIBCO, they use subject-based addressing. So meaning it goes back to the publish subscribe system that I have shown you earlier on in the previous slides. So what happened here is the receiving message on subject X is only possible if the receiver had subscribed to X. And the publishing a message on subject X or message is sent to all currently running subscribers to X. So for example, here the diagram shows how hardware and software work together on a network. So every computers, every machine have RV daemon. Okay, so RV daemon ni is a background process that handles networking part, and they also have RV library. So RV library is the software interface. So basically the system use subject like subject A, subject B, Okay, subject A, subject B, so they use subject rather than IP address to communicate to each other. Okay, so what happened here is the first computer here publish a message on subject A. So they publish kat sini subject A. So the message is sent as a multicast, meaning it will hit all nodes on the line. Okay, so every node. So only the nodes that has specifically subscribed to A. So which one? So example ni PC1 ada 5 PC. So PC machine 2, machine 3, machine 4. So all of this, okay, we receive it, we receive A, subject A, via the RV library, okay, and receive it, and they can process the message because they subscribe to the subject. So the nodes on the fifth machine here, they do not subscribe to A, but they subscribe to B, right? So it will completely ignores the A message. So with this, allow very fast communication without needing central server to manage the list of address, because they just depends on the publish subscribe system. So it's kind of like, the analogy is like radio station. So we have the broadcaster as publisher, and then the broadcaster sends a signal out on frequency A. So on frequency A, like radio era, guna frequency A. So only the people who have turned the radio to frequency A will hear it. So the one who turned the radio to, that is the subscriber. Okay, this is another example, another distributed coordination based system, which is LIME. Okay, so Java Space and LIME actually comes from this, Java Space comes from Genie, right? But LIME comes from Linda. I've said earlier on, Linda and Java Space is like two famous distributed coordination based system. But the difference is why we do not have Linda here, because we want to show different application of the system. So LIME is actually Linda in mobile environment. So this is an acronym, it's the abbreviation of Linda in mobile environment. So we got the name is LIME. So it is a middleware, but specifically designed for mobile and wireless. So basically here, this is about wireless or mobile communication. So in LIME, every mobile device had its own local database. So every node here, we just said like wireless mobile device. So every mobile device has its own data space. So when P and Q, okay, P and Q is the process, are in each other's proximity, so the data space becomes shared. So published data item are stored locally until removed. So process P can publish data items from a specific process. So reactions describe what to do when a mesh is found. So basically here, this allowed two devices P and Q to share data seamlessly while they are in proximity in each other, but they regain their private data once they move apart. So the application of this is like Bluetooth sharing. So when you and your friend are in the same room and your phone sees each other, so basically you can share a folder or share a file. But when one of you walk away, so the connection will break and the shared folder will also disappear. So next we have um, another application. It's not application, another implementation, because the things that we have discussed so far are in the implementation will be in enterprise network, in one LAN, right? So one single area. But what if that we need to coordinate across wide area network? So here when coordination framework operate over wide area network, so the main problem is the scalability. So scalability will becomes a challenge. So so in here we need efficient routing mechanism, and we cannot rely on centralized solution. But so far, we never discuss about centralized solution pun, because we in the distributed coordination based system we relies on middleware to provide the data space, provide data space for shared data space to the processors and machine. So the efficient routing ada dua cara. There's two ways. The first one is naive and second one is refinement. So for naive, it means that you broadcast every subscription everywhere. Okay, so basically you just broadcast the subscription, but this will it will create another problem because it creates too much traffic. So the smarter solution is refinement. So refinement is we is the router need to maintain compute and need to maintain filters, install filters. So what is filters? So filter ni it will control which message should be forwarded based on their content or subscription. So that's why nama dia content based routing. So in content based routing, filter will be stored inside the router or middleware nodes, and the typical content based routing system is like Sienna, and also TIP-QRV pun is a content based routing also. So basically the advantage is the subscription are distributed intelligently rather than broadcast to everybody like in the naive solutions. Router decide which paths are relevant and messages are forwarded only when necessary. Basically, this will improve scalability of the system. So say for example this diagram. So this diagram illustrate naive content based routing approach. So basically the number here represents the number of routers and path over which message may travel. So basically the diagram demonstrate how broadcast behavior akan terpaksa flat lah sebab you terpaksa hantar to all, bukan terpaksa hantar to all. So now let us talk about replication. So under replication kita ada static replication strategy, kita ada static and also dynamic. So let's talk about the static approach. So for the static approach, every piece of data is replicated to all machine. We replicate data items to all machine, every piece of data. So if we look into the diagram, so there are two parts, A and B. So basically, when tuple is written, so it must be broadcast to all machine. But when a tuple is removed earlier on, we use take state. So the delete must also be broadcast. So both when you write, when you do the when tuple is written to the space, so we need to broadcast to our machine. But when you remove it as well, so the delete also must also be broadcast. So hence the reason kalau you tengok sini, so ini semua adalah proses write. So saya akan broadcast kepada semua. Yang bawah adalah proses take. Proses take ni adalah proses delete. So they will broadcast kepada semua. So in this diagram, tuple broadcast means writing requires sending to all nodes. Tuple delete, so removal also trigger message across the network. So static replication works best when data rarely change. When data rarely change, so we can do static replication because it will create because write and take every time you do write and take, so you need to broadcast to all, so it will create unnecessary number of message across the network. So we need to minimize that. So hence the reason why static replication was best when data rarely change. Now, so to balance the read-write operation, because we want to avoid too many broadcasts, so this we need to find the balance between the cost for reads and writes removal. So we organize data space as 2D read. So example, here in the diagram, nodes are arranged in row and column. Okay. So the rule is a write a writer, so anybody who wants to write, broadcast only along its row. So dia akan broadcast kepada dalam row yang sama sahaja. Dia tidak perlu broadcast kepada semua dalam network. And if they want to read, okay, they broadcast to along its column. So pertama sekali kita ada node ada banyak machine. Okay, node is machine. So when you have lots of machines, so we organize it. Sorry. So we organize it in row on columns in matrix form. Okay. So then the rule is if somebody want to write, so they need to broadcast it. If any node want to write, so they need to broadcast along its row, and if they want to read, they need to broadcast only along its column. So say for example, A writes a data item. So in this example, process A writes a tuple, data item tuple. So when A writes, so they need to broadcast it to its row. Okay, broadcast along its row. So here you see in its row, we only have process C. So C received it. Okay, C received the broadcast. And then B wants to read it. Alright, so when according to the rule that I have said earlier on, so if B wants to read it, so they need to broadcast along its column. And again, in this column, C received the broadcast. So when the row and the column intersect, so the write node receive both the write and the read, and the matching can be resolved. So this reduces network traffic while still enabling full write and read access. So lastly, let us talk about the dynamic replication. So for the dynamic replication, the observation is not all data items are equal. So why not all data are equal? Because some data becomes popular and needs many replica. We don't have to replicate everything because because not every data are equal. So some data becomes popular and needs many replicas. Some data is rarely used, rarely accessed, and doesn't need wide replication. So instead of replicating all data equally, so what happened here is we can monitor access pattern. So how many often items are read or write, and we can determine which types of data should be replicated more or less, and adjust replication accordingly. So that's why here the decision of replication must be per type basis. And the improvement that we need to do is let the central component observe the pattern, the history, okay, the history of the read and write, and decide on replication strategy. So basically, this is the self-replication strategy. So this diagram breaks the system into few components, which is the first one is the distribution manager. So we have distribution manager here. Okay, so what distribution manager does, they decides replication level, and then we have the policy table here. So the policy table is the table that keeps replication rules. For example, such as do we want to do we need to do the rule of replicate everywhere, or replicate to nodes that read often. So or keep only one replica. So what are the rules that we want to what are the policy that we want to apply? So the policy table will tell the distribution manager what strategies are allowed. And then we have data space slice. So data space slice ni kena ada sebab each node does not store the entire data space. So instead, each node stores a slice. Slice ni maksudnya only a portion of the full data that is high demand. So this will prevent wastage of memory and reduce unnecessary data duplication. So in practice, the the dynamic replication works like this. So first, application. Okay, wait. My mouse is not really working. Okay. So basically, application here, I don't know why I can't point to the. Okay. So application writes or read data. Okay. And then we have the invocation handler which intercepts the request. So distribution manager akan check policy and usage pattern. So the system will decide what are the policies because tadi distribution manager dah tengok usage pattern, so the system will decide the policies that they want to use. Either they want to replicate more copies or update replicas or serve the nearest replicas. And then replication or retrieval occur via the network plus the data space slice ni lah. Jadi everything is adaptive and automated. So this is a self-managing approach that allow optimized performance in dynamic environments. So with that, it's the last slide. So I'll stop my lecture now. So see you in the next lecture.